Hello, everyone. My name is Amy Hawkins. Thank you for waiting these couple minutes for us as we worked through some flank speed technical difficulties. I want to welcome you to today's Open Environmental Restoration Resources webinar on tools for enhancing reagent delivery to address matrix diffusion in low permeability geologic matrices. Our speaker today is Dr. Neil Durant. Neil is a vice president and senior principal at Geosyntec Consultants, with a practice specializing in the in situ remediation of chlorinated solvents and emerging contaminants in soil and groundwater. Among many other accomplishments, he has led site investigations at more than 120 chlorinated solvent sites and led design of over 70 in situ remediation systems using enhanced in situ bioremediation, in situ chemical oxidation, or in situ chemical reduction. Neil will be presenting on the challenges of remediation at low permeability sites and how to address them. This also includes several case studies and specific examples of various technologies that were used at federal facilities, including the DoD. At the end of the presentation, we will have a Q&A session. We highly recommend that you submit your questions throughout the presentation via our chat box. This presentation is being recorded, and the PowerPoint presentation and recording will be posted onto our public website. Following the webinar, a link to a short survey will be emailed to attendees and registrants. Please fill out the survey as it is our main feedback mechanism and should take less than 2 minutes to complete. Next slide. I want to remind you that participation on this webinar is voluntary and to emphasize the following important disclaimer. This webinar is intended to be informational and does not indicate endorsement of a particular product or technology by the Department of Defense or NAVFAC EXWIG. Although every attempt is made to provide the most accurate information, there is no guarantee that any technology or product will be suitable for your site. Next slide. Before our speaker begins the presentation, I would like to invite Melanie Quito from NAVFAC headquarters to say a few words about the OER2 webinars.
Thank you, Amy. Hi, my name is Melanie Quito. I'm the Environmental Program Manager for the Restoration Program at NAVFAC headquarters in Washington, D.C. And I just want to welcome everyone and also thank everyone for participating in our Open Environmental Restoration Resource webinar series, which we also call the OER2. So it's hard to believe, but we've been doing this for 10 years, since 2014. And the reason why we do this is we always think it's so important to be able to share all of our vast experiences that we have with everything. So this is really for everyone who does this for a living, the RPMs, RTMs, contractors, and anyone who really supports our environmental restoration program. What we want to get out of this, and what we hope that you get out of this too, is the way that we have some type of a venue, which a two-way communication. So number one, we like to share what we have or what anyone wants to teach folks. And we also hope that you share back to us. So it is a two-way communication with that. So with that, we hope to actually show and teach folks of innovations, of our policies, guidances, technologies, practices, and lessons learned. So feel free, and such as what Amy had mentioned, this is all voluntary. So we do really rely on you out there, such as what Neil has done for us, is to provide a topic that everyone can actually share for everyone to learn from. So I'm super excited for today's presentation. It is going to be on the tools for enhancing reagent delivery to address matrix diffusion of low permeability geologic matrices. Whew, that's a lot. And well, so all the people out there, to me, I found it very informative, especially if you have sites such as clays and silts, where you just go, gosh darn it, it's just so hard to get anything done here. It's just so stubborn. And what can you do, right? And I know everyone out there is going, yeah, I can see that. So I learned a lot from it. I hope that you do. And so without any further ado, I'll pass it off to Dr. Neil Durant.
Thanks, Melanie, and thanks a lot, Amy. Thank you, Ramona, Irie, and Tony Danko, Kim Parker-Brown, the Navy team that helped put this presentation together. It was a lot of great contributions from the Navy and NAVFAC XWIC for really supporting and motivating this. Yeah, and thanks for everybody that signed on and registered for this presentation. Hopefully, you find it interesting and learn something valuable for your projects. There is a number of acronyms on this presentation, some of which you've probably seen before, some maybe you haven't. AN for anode, CAT for cathode. EK is electrokinetically enhanced remediation. EK bio is electrokinetically enhanced bioremediation. ISKR is in situ chemical reduction. Low K is low permeability, low hydraulic conductivity. LPZ is low permeability zone. M&A, you've seen that. PRB, you've seen that. ROI, radius of influence. SVE, soil vapor extraction, and ZVI, zero valent iron. So you're going to see some of these acronyms throughout this presentation. Before I get into the tools, I want to, and the problem at hand, I want to sort of start off by some discussion we've had on the Navy team about when do we want to remediate these low permeability sites. They're not going to be it's not going to be cost effective to pursue complete remediation in every case. So about 10 years ago, a paper was published, or 12 years ago, a paper was published by a team of experts in the journal Environmental Science and Technology. And they looked at this problem of chlorinated solvents diffused into low permeability deposits, and what they drew some interesting conclusions. One, back diffusion can limit the performance of any in situ remediation technology, or the only technologies that would always work would be in situ thermal treatment or excavation. But because of back diffusion, we have this problem of getting to 100% cleanup. So a common strategy at a lot of these sites is to pursue partial source zone treatment. And we're seeing that in a number of cases, regulators as well as practitioners are having a greater level of acceptance for partial source zone treatment. So that's something to consider when we think about cleaning up these low permeability sites. This case study at Naval Base Kitsap is instructive about an example where it's very difficult to clean up the site, and even partial cleanup is not going to get us all the way to the end. So in this case, in green, we have a source area with very high concentrations and low permeability deposits, and we have a down gradient plume. GSI did some modeling with the RemChlor MD modeling package. The MD stands for matrix diffusion, and they looked at two scenarios. So on the top graph on the right, we see a scenario where they simulated what was happening at the plume boundary under a no remediation scenario. For vinyl chloride, VC, what their simulation showed was it would take 600 years to get, 6 centuries to get to the remedial goal for vinyl chloride. And then in the lower graph, they simulated what a 90% source removal might get them. 90% source removal only reduced the remediation time frame by 25%. So this illustrates that even when we're remediating the majority of a source area in some of these low permeability deposits, we can still have a long-term source, but it's very difficult to get all the way to the end. So I just mention this because we're not necessarily advocating, we don't want to advocate cleanup of these low permeability sites all the way to the end with engineered methods. We're often the case we want to incorporate monitored natural attenuation or PRB. So the National Research Council also looked at this problem and published a book on it about a decade ago. It was a book on remediation of complex groundwater sites. And they were asked the question of, have asymptotic concentrations been attained? And looking at that to find out, well, when do we stop doing active remediation? When can we transition to monitored natural attenuation or a PRB? And when you think about on the right-hand side, sort of the process for remedy selection. So we do a feasibility study, we select a remedy, we implement the remedy, and then we operate it for a number of years. We start doing our 5-year reviews. And then we start looking at, well, how are we doing? Is the remedy productive? Is it achieving cleanup standards? if we haven't achieved cleanup standards, we should start asking the question, well, have asymptotic concentrations been achieved? Are we sort of gotten as far as we're going to get in terms of cost effectiveness? If the answer is yes, we have achieved asymptotic concentrations. At that point, we should think about transitioning to away from active remediation over to M&A or another passive management strategy, such as with a PRB. So I just wanted to give this sort of backdrop before we dive into the problem and the tools for solving the problem. So with that, let's move to the problem at hand, which is, these graphics are from Camilla Christensen's her PhD work at the Danish Technical University. So if we have chlorinated solvents that are spilled on the ground surface, they sink down into the aquifer, and a lot of clay, low permeability clay deposits are fractured. So in this case, she's drawn the solvents sinking through fractures in the clay. And then if we blow that up on the right-hand side, in early time, what we see is when we have high concentrations of solvents in the fracture, they diffuse out into the clay. And then in later time, on the lower part of that graphic on the right-hand side, we see when concentrations in the fracture or in the transmissive zone go down, that we have back diffusion out of the clay into the transmissive zone. At this point, we have a situation what we refer to as matrix storage, where solvents are stored within the clay matrix or the silt matrix. This slide illustrates these same concepts, but in a little more in a different way. On the left-hand side, we've got a geologic cross-section, early time, solvent spilled, sinking through the unsaturated zone down into a clay. And then in middle time, in the middle of the slide, we've got the solvents diffusing out from the fracture, out into the clay matrix. And then on later time, on the right-hand side, the solvents, which are now stored in the clay matrix, have become a long-term source, and they can leak slowly into an underlying aquifer, and this is what we see at so many sites. Just looking at the problem a little bit further, the graphic on the left-hand side is an example of some of the persistence of a chlorinated solvent plume. So this is a TCE plume at the MEW Superfund site, 1992, a large regional plume, and then we compare that against 2009, 17 years later. What we see is that although concentrations have gone down in the core of the plume, there is just a long lingering sources here, and then the overall dimensions in the plume really haven't changed that much, and that is symptomatic of a typical matrix diffusion type site where things there's a long persistence, a long tail before cleanup. Moving to the graphic on the right, over 30 years ago, my colleagues Chang-Shen Liu and Bill Ball published a paper evaluating the effects of pump and treat on cleanup of a mixed aquitard type system. So these are PCE profiles in soil, and you see on the left-hand side, these were concentrations before pump and treat, and on the right after pump and treat. And what we see is PCE concentrations in their system after pump and treat went down very nicely in the aquifer. They were able to remove. Pump and treat removed the PCE from the soil in the aquifer, but in the aquitard, the low permeability layer, pump and treat really did not move or reduce the PCE concentrations in the aquitard. It basically had no effect. So this problem has been recognized a long time, and we're still trying to come up with good solutions to solve it. A second aspect of the problem is the conventional methods for trying to inject things into the ground. Conventional methods for injecting things into clay really don't work very well in a lot of cases. We need a better mousetrap because these conventional methods they can be chaotic. There can be uncontrolled or unplanned fracturing that happens, or where things go in the ground once you start injecting. There can be daylighting at the ground surface. We see this pretty commonly at a number of projects. There can sometimes, when you inject things under pressure, they can end up in neighboring monitoring wells far away from the point where you've injected them. We've also seen if you inject things in some of these wells, they can end up just stuck on the bottom of the well and not really go very far. We've seen all of these problems. So we need better tools for getting reagents into the ground, and that's what the rest of this presentation is going to focus on. When we think about this graphic is from a paper, Brooks et al. On groundwater monitoring remediation a few years ago, and it summarizes the tools that we have at hand for addressing contamination in these low permeability deposits. Moving from left to right, we're moving from the simplest, lowest capital cost options, and these graphics don't account for O&M costs, but they move from the lowest capital cost to the highest capital cost, and from least difficulty to greatest difficulty or complexity. And I think by complexity or difficulty, we're talking about technical specialization. But moving from the left, our options, there's always M&A or permeable reactive barriers, and then moving to the green circle, what we call amendment to forward diffusion, where we're injecting in situ reagents, either by direct push or by fracturing. Moving to the yellow circle to the right, physical alteration of the low permeability zone. Architecture, we do that by soil mixing or by excavation. And then further to the right in the red circle, where we are moving into active remediation with thermal remediation, electrokinetics, and those are really treatments without permeability limitation. So those are the brute force options. So in this presentation, we're going to be focusing on electrokinetics, soil mixing, fracturing, and then implementation of high resolution reactive columns by this bomber technique that Steve Richardson at GSI developed. So let's move into electrokinetically enhanced remediation. This is a technology that's been used at 4 different federal sites that we're aware of, and we're going to show you a case study. Some terms for EK. So what EK is the application of a low voltage direct electrical current to the saturated subsurface via electrodes, anodes and cathodes, and establishment of an electrical flow field. Once we have the electrical flow field established, we can move amendments, treatment agents, in situ treatment agents in the target treatment zone by processes such as electromigration, which is the movement, induced movement of charged ions, electroosmosis, which is the bulk movement of water, or electrophoresis, which is the movement of charged colloids or solid particles. EK really has a lot of benefits over hydraulic amendment as permeability goes down, and because it really relies on the electrical properties of the soil. It doesn't rely on the hydraulic properties of the soil. So looking at the graphic on the right, we see how permeability decreases over grain as grain size decreases in a series of sedimentary deposits. So moving from fine sand on the left to bentonite on the right, as we move down that ladder, the hydraulic conductivity goes down 5 orders of magnitude. But as the hydraulic conductivity goes down with decreasing grain size, the electrical conductivity essentially stays the same. And the electroosmotic permeability basically stays the same because these properties are independent of the permeability, and we can take advantage of that when we're trying to do in situ remediation. That's what EK does. This graphic sort of summarizes in a simple way the relative transport rates for different mechanisms. So if starting at the top for advection, we're not really going to be able to move water or particles via advection in clay very quickly at all if advection alone is all we're doing. But looking at electromigration on the bottom, we could achieve rates as high as 1 meter a week by applying that electrical current. So the difference between electromigration and advection is again, it's 5 orders of magnitude, just vast, significantly faster migration of delivered amendments with electromigration. How is EK implemented in the field? Well, it's implemented with a series of electrode wells. So these can be PVC wells in which we insert electrodes and apply electrical charge and set an anode and a cathode. And then between the electrodes, we put in an amendment well to deliver in situ treatment agents. And that can either be directly within a clay, as shown on the left, or maybe within a heterogeneous series of deposits with alternating sand and clay. So either we've applied that in both of these types of settings. A case study was done at Naval Air Station Jacksonville as part of an ESTCP project. This was a site where we had a persistence of PCE, tetrachloroethene. It was stored in a clay deposit some 19 to 23 to 25 feet below ground surface, and that profile on the left-hand side shows in the gray where that coincides with the high PCE concentrations. We were having difficulty getting that out of the ground by other means, so the ESTCP sponsored this demo of EK, and the graphics on the right show the simple layout of the pilot test plot or the demonstration plot. There was 9 electrode wells and 8 supply wells in an active parking lot. This slide summarizes a lot of the parameters of the setup of this demonstration project. You can see on the right-hand side, that was the construction installation of the electrode wells and supply wells at the Naval Air Station Jacksonville, as well as the control trailer and control system on the lower right. But this was a 35 by 35 target test area, 9 electrode wells. The electrode wells were spaced about 17.5 feet apart. We had 8 supply wells. As mentioned before, the electrode wells were PVC cased, screened between 19 to 23 feet, all within clay. The electrode was a titanium rod with a mixed metal oxide coating. There was a direct current supply unit, which would receive 120, 240 volt, 3-phase alternating current with an output up to 24 amps or 250 volts. And this is a little more on the approach, the test approach at Jacksonville. The test was performed in 2 stages. There was each stage was 5 months, and then there was a 6-month downtime between the 2 stages. But the stages differed, but there was a reversal in polarity. And in stage 1, the polarity, the electrical field was moving from left to right, and then in stage 2, the electrical field was moving from top to bottom. And the power consumption over the total duration of the test was about 1,600 kilowatt hours, which was the same as the equivalent of 200-watt light bulbs running for that same duration, that 10-month period. Lactate was one of the amendments. pH buffer was an amendment. The pilot test was also bio-augmented with dechlorinating bacteria. And there was no overpressure injection. It was primarily a gravity delivery injection. And here's a sort of summary of results. There was 3 performance monitoring wells within the pilot test plot. And just high-level summary of what we saw, there was effective distribution of amendments in the clay. The total organic carbon increased 8-fold. And this, remember, we're adding electron donor, we're adding lactate, so we really want to increase the total organic carbon, and we succeeded there. We stimulated dechlorination of PCE to ethene. We saw increased ethene everywhere we looked for it, and we stimulated significant growth of dechlorinating bacteria by as much as 3 to 6 orders of magnitude. So looking at the graph there in the middle, the EKMW01, starting with the green diamonds. Those are Dihalopicoides bacteria, and the blue squares are vinyl chloride reductase genes. So these are both biomarkers for detection of dechlorinating bacteria. We saw that these increased very nicely over the 2.5-year monitoring period. We also saw a lot of production of ethene, which is in yellow. We saw PCE concentrations decrease between 70 to 90% across all 3 monitoring points. And we saw a lot of production of monochloride. So this test was not designed to get all the way to the end. This was just a demonstration and it was ESTCP was pretty happy with it, as were we. It successfully demonstrated EK as a technology for low permeability sites. Next tool we want to talk about is hydraulic fracturing. And this is, of the options presenting you today, this one is probably the most mature, used most widely at DoD sites. We identified 12 different federal sites where this technology has been used. And hydraulic fracturing you can think about it in terms of the Darcy equation, where Q is volumetric flow, K is hydraulic conductivity, A is area, and DHDL is hydraulic gradient. But what we're doing when we're doing hydraulic fracturing is we're increasing the surface area for injecting things in the ground, and that enhances the flow of what we're injecting and enhances the distribution of what we're injecting. So on the left-hand side, we have a simple graphic of it. Say if you compare a conventional injection well, a 2-inch well, 8-inch borehole, a 10-foot screen, in a 12-foot sand pack, that would have, say, a calculated surface area on the order of 25 square feet surface area. But when we do hydraulic fracturing, and we get what we typically get is a 15-foot radius fracture, sand fracture, and looking at the upper and lower bounding surfaces for that fracture, we can increase the surface area up to 1,400 square feet of surface area for each fracture. So we really can vastly increase the surface area for delivering things to the subsurface and allow for enhanced flow. So this case study at Lake City Army Ammunition Plant, where enhanced fracturing was used for in situ bioremediation, illustrates some of the benefits of fracturing. So this is a site where there was a former oil and solvent waste pit. There was TCE and silty clay, sort of a residuum, weathered shale, 25 to 40 feet below ground surface. At this site, there had been about a decade of injecting electron donor via conventional wells. And then later, between 2015, about that time, and then on into 2021, 10 fracture wells were established, and that included about 3 to 4 fractures per location, for a total of 37 fractures. And we were able to see the effect of fracturing on improving delivery of reagents. So at this site, in the picture on the right, the 10 fracture locations in the orange circles are shown on the right. This graphic shows flow rates for injected bioremediation agents. In green, we're seeing the green bars are the injection rates in conventional wells, and the blue bars are the injection rates in fractured wells. So what we saw was in the fracture wells that their ability to accept what we were injecting was at least more than 10 times increased in terms of average flow rate relative to the conventional wells. So we're able to get a lot more stuff in the ground and get much better distribution in this low permeability setting. Some results for this case study in most places in the monitored, and this is sort of a biobarrier type configuration, if I didn't mention that. In most places, we got more than 90% enhanced treatment of the solvents across the plume. But there was at least 2 locations where a persistent NAPL reduced the rate of treatment. And so that, because this was a biobarrier configuration, not a source area carpet bombing, it didn't go for everything, but we got very good performance within the PRB itself. I'm going to move to another case study for hydraulic fracturing for treatment of 1,2,3-trichloropropane by in situ chemical reduction, ISCR. This is at Camp Pendleton Navy site, Marine Corps base in California. And this is an ESTCP project. And so at this site, 1,2,3-trichloropropane, the concentrations in groundwater were about 1 part per billion. but that was still high above the California cleanup level for trichloropropane. So the contamination was hung up in heterogeneous silts and clays about 30 to 65 feet below ground surface. And the design team tested and successfully demonstrated that the trichloropropane could be completely treated with zero-valent zinc. Zero-valent zinc is a very strong reductant. It is stronger than zero-valent iron, and it can successfully reduce, and it's shown in the graphic on the right, it can reduce trichloropropane sequentially, cleaving off the chlorines from the propane molecule. And the objective is to get all the way down to propene is an innocuous end product. But for this project, in the end, and as I'll show you, a full-scale zero-valent zinc PRB, permeable reactive barrier, was installed, and by direct push jet injection hydraulic fracturing. So this is hydraulic fracturing that's performed with a direct push rig, and that injected over 70,000 pounds of zero-valent zinc at this site. So this graphic and this next slide shows concentrations of 1,2,3 trichloropropane before remediation on the left-hand side. So again, these are concentrations on the order of 1 part per billion, but they're still 100 times above the California cleanup standard. So the conceptual design was to install a zero-valent iron PRB injected in 14 hydraulically fractured points across the plume, shown on the right-hand side, at target depths down to 65 feet below ground surface, about 15-foot target radius of influence. And here's some example results. So on the left-hand side is sort of a isocontour map of the TCP before treatment. In the yellow, we see where the target injection areas were. And again, concentrations for TCP range from 0.1 to 1 part per billion or higher. So that you see the baseline on the left, and on the right-hand side, we see performance after 1 year. And after 1 year, we had treatment down to non-detect in a number of, at least about half of the PRB, but in general, concentrations across the site were reduced some in the neighborhoods of 90%. Very successful demonstration. This is another project where the technology was not. This was not a project that was aiming to demonstrate complete cleanup of the site. It was more of a technology demonstration. This was also deemed a success by ESTCP and the Navy. So that's it for fracturing. I'm going to move on to another tool, in situ soil mixing. And we identified 7 federal sites where in situ soil mixing has been used, but I think the list is actually probably a lot longer than that. But this we were able to go over seven examples. And if you're not familiar with soil mixing, this slide illustrates simply how it works. So you might start off as a graphic, say on the left-hand side, where we have a DNAPL source area where DNAPL has sunk down beneath the source area, and maybe it gets hung up on a low permeability layer. And then in the middle, the technology is pretty simple. We have a large diameter rig where we might auger in columns of reagent treatment material that could be granular iron. It could be granular iron mixed with bentonite. And so we'd use a large diameter auger to accomplish that. And then once we're done, we may have something left of what's shown on the right-hand graphic of a series of columns where the contamination once stood, but it's been altered by the mixing of the deep soil rig and maybe any treatment agents left behind. So when we talk about in situ mixing, there are at least 2 different types of in situ soil mixing. On the left, we see a picture from Site 88, Marine Corps Base Camp Lejeune, North Carolina. That picture is almost 20 years old, I believe. At that site, it was a zero valent iron clay remedy. They got very good treatment results, by the way, but it is a messy type of in situ soil mixing. It's a messy technology. You can see that straight away. On the right is a different type of in situ soil mixing technology, and that is it's steam enhanced application of zero valent iron and guar. So for the option on the right, it combines both implementation of a reactive media such as zero valent iron, but they're also pulling out vapors via soil vapor extraction and using steam to enhance the whole process. So it involves a component of recovery of chlorinated solvents as well as a component of in situ treatment. Then that picture on the right is some off at Air Force Base. So I want to go over a case study. I think it's one of the best out there for deep soil mixing with zero valent iron, steam, and air. This is SMU-1 from the Department of Energy Gaseous Diffusion Plant, Paducah. And you can see on the left, this is the rig that was used to do the mixing, the crane and the soil mixing assembly, and that there's a SVE shroud. That black shroud around the auger is what's used to extract the vapors, and that's shown a little bit better perhaps in this picture. And then we have a large multi-blade rotating mixing and injection tool. This graphic here presents a lot of information, but I think it's worth a look. To summarize what was done out there at SMU-1 at Paducah. So it was a former oil land farm, a maximum treatment depth down to 60 feet. They installed about 258 soil mixing columns of 8-foot diameter. And it's not obvious to you, I'll just mention that this project was really a very large scale remediation, which differs from some of the other projects I just showed you, which were more some of which were just pilot scale technology demonstration. This was a full scale implementation. Steam, air were injected, soil vapor extraction was applied. Almost a million pounds of zero valent iron were put in the ground in these columns, 17,000 pounds of guar. Looking at the graphic on the right, you can see how these columns overlap to one another, and in the purple rings in the center of the treatment area had a 17.5-foot overlap, and that overlapping is used in the highest concentration areas where we want to affect the most treatment. As we move out of that area into the blue columns, that's where we might have a 10% overlap, and on the outer perimeter, it's a 0% overlap in these borings. I just want to also mention that the in situ soil mixing does entail some level of destabilization of the soil, and so in this case, 278,000 pounds of quicklime were added in the upper few feet to stabilize the surface soil after treatment. So here's some treatment results for this project, and they great treatment results. By comparing TC and soil borings before and after treatment, there was a 99% reduction in TCE. On the graphic on the left, we have maximum TC concentrations. The dark blue bars are pre-treatment and the hashed bars are post-treatment. And we had a multiple order of magnitude reduction in concentrations in the maximum TC concentrations, and even better results when we took the arithmetic mean of soil measurements. So it definitely achieved treatment objectives in this project. I'm going to move to tool number 4, and this is what we'll call closely spaced reactive columns. This is also known as bomber technology. And I would acknowledge Steve Richardson and the team at GSI for leading the development of this technology in this project. So this technology was inspired by the graphic on the left. What you see is an excavator equipped with a specialized stitcher mast, and this is a tool called deemed the grout bomber, which was used for fast inline delivery of grout columns to stabilize shallow, geotechnically unstable soils. And the graphic in the middle, cartoon in the middle, sort of illustrates that. So what GSI thought of doing was repurposing this grout bomber to, instead of injecting grout, they were going to inject in situ treatment agents like zero valent iron, vegetable oil, sand, and then use that and deploy it into low permeability deposits to facilitate back diffusion out of clay. And the graphic on the right illustrates that. GSI did some modeling with ModFlow and MT3D to evaluate how this technology could perform in a model system. So the model system shown on the left is a clay that consists of, say, 20 milligram per liter of chlorinated solvents, and there's a sand above it and a sand below it. And looking at the graph on the right, we see that if nothing was done to clean this up, this clay, it would take at least 500 years to reach cleanup standards. But if these columns are installed, these reactive columns are installed with a 2-foot spacing, 2 feet apart, these columns could enable and facilitate attainment of MCLs within less than 3 decades. So that's what their modeling showed. This figure shows a summary of the design of the system, our pilot test design, and this was done at Navy site Indian Head, Site 17 in Maryland, where in purple they injected across the whole site over 800 vertical reactive columns. In purple, they were 700 zero valent iron sand columns, and in blue there was 100. In a subset of the area, there was 100 vegetable oil and sand columns, 39 tons of zero valent iron in total. In the center, there was a 2-foot spacing of these columns where the concentrations were higher. And in the blue area, there was a 3-foot spacing of these columns because the concentrations were lower. And then they monitored performance for about 26 months. And here's some example treatment results. In general, there was about a 70% reduction in TCE concentrations. They saw a lot of TCE degradation products, cis-TCE, vinyl chloride, ethene, acetylene. Remember, this is another project where this is a technology demonstration. This was not a site-wide cleanup. They were just trying to demonstrate that the technology could work. But I think the part that struck home for me was they got 800 columns emplaced in 8 days. Just a really remarkable speed of emplacement of this reactive material. This slide here summarizes much of what I just told you, and I want to try to go through it quickly. What can we take home about these different technologies? Well, electrokinetics, starting at the top. I'd say it's a technology that has low to medium maturity compared to some of the others. We've only seen it tested at 4 sites. I'd say it has a medium speed of remediation. The advantage is it doesn't require fractures or preferential flow paths. Its performance is independent of those things. The disadvantage is that it's technically specialized, and it does require some pH management. Its unit cost, treatment cost tends to be middle of the road. It's more expensive, say, than hydraulic fracturing in some cases, but it can be less expensive typically than soil mixing. Moving to hydraulic fracturing, as I mentioned, hydraulic fracturing is probably the most mature of the options presented today, or one of them, and it has a high maturity, but I'd say it has a low speed of remediation compared to the other options. Probably one of the slower acting. It's again, advantages: high maturity, high commercial availability. Disadvantage is it relies on diffusion to bring contaminants into contact with treatment agents. Soil mixing, it is a high technology maturity. Of these options, it is the fastest acting of these options, and it achieves excellent contact between contaminants and treatment agents. Disadvantage, it can be messy. It can leave unstable ground afterwards. And for the thermal, when we're injecting steam, it also has been known to result in what I'll just soil burping, has been described, and it is something that needs to be monitored and managed and designed. It also can be very expensive, but in the bright side, you're in and done, and there is no long-term O&M. And then lastly, there's the reactive bomber, the bomber technology, which I just mentioned. very fast speed of implementation, but it's a relatively immature technology. It doesn't have the same road testing that these other technologies that we heard about today do. It does have a good price tag in terms of unit cost. So let's just summarize what I just presented. Takeaway points. Chlorinated solvents diffuse into low permeability clays and silts, and that's a problem. It's difficult to access these chlorinated solvents that are stored in the low permeability matrices. Once they're in, we can't really pump them out, and it's difficult to inject things into the ground. Conventional hydraulic injection and extraction methods really are not very effective. And chlorinated solvents in these low permeability matrices can serve as a long-term source of CFOCs in groundwaters and aquifers. So we need to expect that there's going to be long time frames for remediation at these sites. Tools you heard about today: electrokinetics, hydraulic fracturing, soil mixing, bomber or reactive columns. These all can be used to accelerate remediation and improve reagent delivery in these settings. However, at some low permeability sites, source area remediation is only going to have a negligible effect on remediation timeframes, and we need to think about that. At some of these low permeability sites, instead of source area remediation, we really should be looking at M&A or M&A plus permeable reactive barriers, and because they can be more attractive, perhaps a more cost-effective approach than trying to go after the heart of the beast. But that is it. Thank you so much for your time. Oh, wait, one more thing. Sorry about that. There's a lot of resources out there that have been put together by the Navy and other DoD agencies. A lot of resources that are publicly available on the internet to learn more. And here are some references for my presentation today. I want to just point out that all of the case studies presented the information was derived from publicly available documents available on the internet, published and released with approval. That's it. Thank you.
All right. Thank you, Neil. We've been collecting the questions that have been submitted throughout the presentation. Anyone who has additional questions, please feel free to submit them now. The first one that I wanted to ask is, for the EK applications, are there other types of in situ treatment agents in addition to bioremediation treatment agents that can be used?
Yes, thank you, Amy. We can use oxidants such as permanganate, sulfate, ionically charged. That's the key there. When we're using electrokinetics, we want to add charged treatment agents, and that's the same as the bioremediation agents we added, because in the case study I showed, we were adding lactate, which is an anion.
Okay, thanks. Same question, but for fracturing, what other types of in situ treatment agents can be injected there?
So we saw case studies for injection of zero-valent zinc and injection of liquid bioremediation amendments. Well, one of the case studies was emulsified vegetable oil. So with that technology, there's a lot of case studies out there with microscale zero-valent iron. So that's another one that there's been a lot of use of that. We can inject permanganate is another one, or persulfate. And I think increasingly the DoD is funding a number of projects at delivering colloidal activated carbon or granulated activated carbon into clay matrices. So yeah, a lot of different options there for amendments to be delivered by fracturing.
Oh, okay, thank you. All right, another question we have is, for the grout bomber, what is the maximum injection depth?
I don't know what the maximum injection depth is, but the injection depth for the case study that we saw was down to no more than 40, but I'd say between 30 to 40 feet below ground surface. But it could be more. I think the best answer may reside just looking at what's been done with the grout bomber by Haywood Baker, or how they're doing their grout injection for geotechnical stabilization.
All right. Thank you for those of you who submitted those questions. And thank you, Neil, for sharing your experiences in addressing these low permeability sites. If you submitted a question that we didn't get to, or if you have a question that you didn't get a chance to put in, you can reach out to Neil or to one of the Navy points of contact on this slide at the email addresses shown here. Next slide, please. As we wrap up, please take the survey that will be emailed to you following the webinar. The survey should take less than 2 minutes to complete, and it provides us with valuable feedback. You can stay tuned for our next OER2s through the T2 email. If you're not receiving our T2 email already, you can put a message in the chat box in the Q&A asking to be added to the list. You can also follow us on LinkedIn for the same announcements. We get the word out both places. We also wanted to let you know that we post our OER2 presentations and recordings to the Go ERB website and on YouTube for the recordings. So make sure you check out those pages. And then I just want to thank you all again for attending this OER2 webinar, and we look forward to having you back next time.
Thanks everybody for joining.